All right. So we have looked at, what have we looked at? We have looked at lots of circuits. And we were looking at Zener Regulator, right? We were looking at Zener Regulator. So let's continue with Zener Regulator. This time we will look at a circuit with a load. Yes, I'm recording. Okay, so this, what is going on? Changed. Okay, all right, so this circuit has a Zener diode connected to a voltage source VSS. Simply just take it as a source voltage. That designation VSS and VDD, that comes from electronics, dual power supplies. Anyway, so we have a load resistor in there, and this circuit, basically, we're going to analyze how the Zener will regulate the output voltage, right? Now, the resistor R that you see in series is basically a current limiting resistor. Effectively, just think about like Ohm's law, V is equal IR, right? If you have a load, let's say you're running a simple LED off of a 1.5 volt battery, right? That LED does not, it's a diode, so it does not have very high resistance. So if you just connect a 1.5 volts to any LED or load, what will happen? Current's infinite, you'll just blow everything out. And so that's why you need a resistor in there. So all electronic circuits will have resistors like these, and they are all known as current limiting resistance. It could be as small as like 100 ohms, doesn't really matter, but it should have some value so that it reduces the amount of current that's, you can control the amount of current that's going through the circuit. So typical of all electronic circuits, you have this current limiting resistor. RL is the load resistor, and then you have VZ connected in parallel. So current limiting resistor, and then RL is the load resistance. Now we are given, let's see all the information. VSS, take a look at my notes. Right here. Okay, VSS is given to us as 24 volts. R is given to us as 1.2 kilo ohms, and RL has a value of 6 kilo ohms or 6,000 ohms. Okay, 6 kilo ohms. And the question being asked is to find the load voltage and IS. We're not given anything else. We are given, of course, the Zener regulator transfer characteristic, okay, VI characteristic. So we're going to perform load line analysis on the circuit. Zener regulator will load, plot it on the characteristic that is given to us, and determine what the output voltage is going to be at that particular operating point. Now, the assumption is we don't know what the Zener voltage is going to be at that particular operating point, right? Typically, that's not the case in real life, okay? But we'll look at that just a little bit later. So first step here, let's take a look at the circuit. If you remove the Zener, what do you see? Just two resistors in series, right? Keep that point in mind. Now, the output voltage, VL, which is across load resistor RL, is also in parallel to the Zener diode. So VL should equal VZ at that point, right? Again, we're talking about voltage regulation, it's in parallel. So since we need to find the value of that Zener diode, the breakdown value, we need to find the Thevenin voltage as seen by that Zener diode. Okay, right now you have two resistors in series, so you don't know what that voltage is. It's not going to be VSS, right? If you look at it just without the Zener diode, this is what we find, right? The Zener diode is connected right here. And when I say right here, it's in parallel connection. So the circuit schematic does not matter left, right, it's all the same. It's all in parallel. Okay, it does not matter where it's connected. So the voltage that is being applied is not the same as VSS. We need to find that voltage. And that voltage is given by the Thevenin equivalent network, or Thevenin equivalent circuit. For this particular circuit, it is as simple as just applying voltage division. Okay. Other circuits, it will be something else. But for this circuit, it's simply voltage division. But essentially what we're doing is we want to take this circuit. We want to take this circuit. We want to go from here to here. And then from here to here. That's what we want to do. Right? We want that one voltage source and that one resistance that is being seen by the Zener diode. How does the circuit appear to the Zener diode itself? Because without that, we cannot analyze. So once we do that, we can have the circuit shown in C, and then we can plot our load line. So quick analysis, Thevenin network. If you want to find the Thevenin voltage, you remove that component and determine the voltage where the component was connected, right? You want to see the Thevenin voltage as seen by that particular component, then you remove that component from your analysis and you analyze the rest of the circuit. So in this case, that Thevenin voltage VTH would be VSS times RL divided by RL plus R. Simple voltage division. Okay, VSS times RL divided by RL plus R. Plug in the values and we solve for that voltage. Okay, so VSS is what? 24 volts. RL is what? 6K, so 6,000. And then R is 1200. 1200 plus 6,000 gives me 7,200. So that is 12. 12 times 2, 4. And that should give me what? 20 volts. 20 volts. 6, 12, 12, 2 times 10. Yeah, 20 volts. Make sense so far? Then we need to find RTH. Sorry, question?
It does now, so we start doing the homework.
Yeah. Well, I'm always there to help if needed. Yeah. RTH. The circuit for RTH, but the first thing we want to do is, of course, Zener diode is gone. Right, Zener is connected here. So it's not part of our analysis. We calculate RTH at those open terminals, meaning we want to find REQ. And you're right. Voltage is replaced with a short. Current source with an open. And you can see R is in parallel with RL. So my RTH is simply R parallel RL. When you have two resistors in parallel, how do we solve them? Well, that's a generic equation. When you have two resistors in parallel, how do we solve them? Should go back and change your grades for 201. At least the ones who took my classes. It's the product, well, no, it's the product of the two divided by the sum of the two. Too late, your grades changed. It's the product of the two divided by the sum of the two. 1 over R1, that's of course the actual equation. It's the reciprocal of the sum of all the reciprocals, but when you have two resistors in parallel, you just product of the two divided by sum of the two. So 1200 times 6,000, 72 divided by 7,200, and 6 12 is 72, cancels out. A million divided by 1,000 gives us 1,000 ohms. So RTH is 1,000 ohms. And there you have it. That's our Thevenin equivalent network that's being applied to that Zener diode, VD. We now write out our equation, KVL around that loop, and that is the equation for the load line. From that, we'll plot it on the characteristic, and we'll find the intersection point, the operating point. That will give us the output voltage. Yes. We don't need the current. If we wanted the current source, yeah, we could do that, but we don't need current. So just depends on what we need, right? Yeah. Okay, so RTH is 1,000. So if I write KVL, in the circuit, I have, what do I have? KVL in C, or circuit number C. I get VTH plus RTH times diode current ID plus the diode voltage gives me 0. Right, minus minus, current's flowing in the opposite direction. Note why I am taking minus, right? The anode of the diode is always the positive reference. It doesn't matter what kind of diode it is. So even though the Zener diode is connected in reverse bias, this again, remember from last class, even though it's connected in reverse bias, the positive reference for the diode voltage will always be at the anode. Okay, and current will always be shown as flowing from anode to cathode. So if current is flowing from anode to cathode, and diode polarity is plus minus that way, then the voltage drop across R or RTH is basically minus on the left and plus on the right. Okay, so it's minus on the left and plus on the right. So when you perform your analysis, you always have to keep that in mind. When we talk about diode voltage, the positive reference is always at the anode. Doesn't matter what kind of diode it is. That's why all Zener voltages, when we performed the analysis last class, it was minus. Remember, quadrant 3. And so when you apply KVL, you simply get VTH plus the voltage drop across the resistor plus the diode voltage equals 0. You now have your equation. So VTH is 20 volts plus 1,000 times ID plus VD is equal to 0. You get the operating point. Plug in ID equal to 0, and you get VD equal to VTH or 20 volts. You plug in VD equal to 0, and you get ID is equal to VTH over R, so you get 20 milliamps. That gives you your load line, the two endpoints of your load line. Think over it 10 seconds or longer, and let me know if you have any questions. Yes. Well, you just have to take it into account when you're writing out the equations, if it ever comes up. Yeah. Yes. Yeah, so VD ID is equal to 0. So minus 20. There, that's the minus. Minus 20 and minus 20 milliamps. I was just answering Jonathan that yes, you have to take into account, and I didn't take it into account. Minus 20 volts and minus 20 milliamps. So there, we took it into account. I have it in my notes. I just didn't write it here. Yeah. Well, I'm doing something right. Students, if students are correcting me, then I'm doing something right. All right, does it all make sense so far? Now we have our load line. Let's go to the next page. You plot, sorry.
So that one was low, like no breaking point.
Yeah, operating point. So now we have our minus 20 and we have our minus 20 milliamps. I mean, sorry, minus 20 volts. This is minus 20 milliamps. This is current I. So just so that it's clear, x-axis is voltage always, and y-axis is always current. Okay. Now it intersects conveniently right at 10. So voltage for the Zener diode, or the output voltage, is 10 volts. So intersection point which is our operating point, is at minus 10 volts and minus 10 milliamps. Therefore, output voltage VL is minus 10 volts. And so for a input voltage VSS of, what was it, 24 volts, our Zener voltage is at 10 volts. So graphical solution. Does that make sense? Right? That's load line analysis. Again, same thing that we did for the diode. Now, actually, VL is not 10. VD is minus 10. VL, VD is referenced this way. VL is minus of VD. So it's actually just 10 volts. Okay, VL is the opposite of VD. VD is minus 10, so VL is just 10 volts, or plus 10 volts. Yes. Yeah, there are circuits where we actually do that. It just depends on your application. Yeah, but we don't use, I mean, load line analysis is just one kind of analysis. So it just depends on, what we're actually looking for. It's just different tools in our toolbox. We can choose whatever you want to analyze with. Yeah. So now IS, finding the total source current, IS is simply you find the voltage across the current limiting resistor, apply Ohm's law, and you can solve it from there. So if you go back to that circuit, IS is the current that is being supplied by the source. It is also the current that goes through that resistor R. So it causes a voltage drop across that resistor. Let's call it VR. Now, if you apply KVL around that loop, you get VSS minus VR minus VL, sorry, is equal to 0, right? Zener diode is in parallel with RL, so voltage is the same, so we don't have to worry about it. We apply KVL around the loop. VSS is supplying energy to both resistors, and so the voltage drop across both the resistors has to equal VSS. So if I apply KVL around the loop, from that KVL, I get VSS minus VR minus VL is equal to 0. therefore VR is simply VSS minus VL. 24 minus 10 gives me 14 volts. And therefore IS is simply 14 divided by, what is R? 1200. And this comes out to be 11.6667 milliamps. You can find the source current that way. And of course, we can also use all of our circuit analysis techniques to find any other current. We can find IL that way, we can find IZ. And I'll solve this example and show how we can actually do that. Yes. Yes. Yes, we can do that too. So to recap, we first begin our analysis by looking at the circuit. We see that there are two resistors in there. It doesn't matter how many resistors we have or how many sources we have. We need to see how the circuit looks as seen from the perspective of the Zener diode. So we need the Thevenin equivalent circuit, the Thevenin equivalent network. We need to know exactly how much voltage is being applied, calculated across the voltage drops. So we find the Thevenin voltage and we find the Thevenin resistance as seen by the Zener diode. Now we have one single voltage and one single resistance, VTH and RTH. Once we have that circuit, we apply KVL around the loop and obtain the load line equation. Once you have the load line equation, you plot it on the characteristic and you find the operating point. That operating point gives you the output voltage or the Zener voltage at VSS is equal to 24. And once you have the output voltage, you can calculate everything else from that point on. Any questions? Any questions at all? Okay. How many of you had the pre-lab, the Zener diode pre-lab? Is it already due? Have you already done with it? Friday. Anyone else left to do? In any case, how did you all solve it? Did you reach out to the instructor? Did you just solve it? Okay. No one came to ask me except for like one student. You can always, yeah, you can always reach out and ask me. It's fine. Even if it's your lab, I'll be happy to help out. Anyway, it is part of the analysis. So finding or determining, let's use the same circuit that we use here. It's a similar circuit to the pre-lab, right? So let's take this circuit and I'm going to go below the example. So determine range of input supply voltage to the circuit above. Okay. And we will assume the Zener diode is ideal and VZ is 10 volts. Okay, is a Zener diode of 10 volts. And again, to keep things simple, PZ max power rating is 1 volt. I mean 1 watt. So similar to your pre-lab question. But again, this analysis is generic. Okay. So we want to find the range of values that we can apply to that circuit. Okay. So first, think about this. If we don't have a Zener in the circuit, what happens? If you increase VSS, the current through the circuit increases. If the current through the circuit increases, the voltage drops across both resistors also increase, right? But now we insert a Zener diode in there. What happens? It should keep the output constant. Even if the input increases, meaning if the input increases, input voltage increases, the current coming from the source increases, but it should keep the voltage at the output constant, meaning the current through RL should not change. So where is the excess current going? It's going to the Zener diode, right? So the Zener diode has a limit, and that limit is described by PZ max, the maximum power dissipation of that Zener diode. Okay, so remember the first slide of the Zener diode, I have like there are two specs. The two most important ones are the Zener voltage VZ and then PZ max. And from the Zener diode, so from VZ and from PZ max, we can calculate what the maximum current the Zener diode can handle. P is equal to IV. Electrical power is always product of voltage times the current, right? So if you have VZ and you have PZ max, you can calculate the maximum current that Zener diode can handle without being damaged, right? If you exceed that, I mean, all of these electronic components, they get hot. Energy is transferred. A lot of the energy is released or dissipated as heat. And so it gets hot, right? So PZ max is basically the maximum it can handle. So the maximum it can handle is basically, let's say we are using 10 volts and 1 watt. How much current? Is equal to IV. 1 divided by, yep, 100 milliamps, right? That's the maximum current the Zener can handle. Then we know the output voltage should be a 10. What is RL? I'm sorry, what is IL? Exactly. So diode voltage divided by the resistance should give us the current that goes through RL. You add up 100 milliamps to that. That is the maximum current that can come from the source. That's your maximum limit, right? Now, I mean, we'll work through everything. I'm going to solve everything. Minimum. What happens if the input voltage is less than 10? Doesn't even turn on. So if you apply like 5 volts at the input, if you apply 5 volts here, VSS, at the output, you'll only get 5 volts. Because the diode is off, IZ should be equal to 0. 0. Nothing should go through there. 0. Slowly increase it. It now crosses 10, maybe 10 ideal diodes, or let's just say 10.00001, like a fraction higher than 10 volts. The diode turns on, right? That is the minimum voltage that is required to turn it on. But again, going back to the first point, if the Zener diode is not there, what do we have? 2 resistors in the circuit. It's a voltage divider network. So the input voltage should be the voltage that appears across RL. Does that make sense to everyone? We want this voltage right here, VL, to be 10 point whatever 001. To keep things simple, let's just call it 10 volts. Right? Let's just call it 10 volts. When you reach 10 volts, Zener diode is going to turn on. So 10 volts here plus whatever voltage drop appears across VR. So the minimum voltage that is required to turn on the Zener is VR plus 10 volts. And that's how we're going to calculate. So does it all make sense? That's essentially the analysis. That's it. That is essentially the analysis. Okay, so let's start with minimum, because that's the easiest. Well, no, the most obvious place to start. Let's not say easiest. So V minimum should be equal to VZ, your voltage, plus, whatever, just a little bit. VZ plus VR. And we said we'll take VZ as equal to 10 volts. So we'll just keep it that. And let's draw the circuit down here. So and VZ is 10. This is going to be VL. And this is going to be VZ, and this is going to be VR. This is going to be V in min. So if I write out the voltage divider expression, I would get from voltage division, I get VZ should be equal to V in minimum times R, or oh, sorry, not R, RL over RL plus R. Okay. So that comes out to 10 is V in minimum. RL is, what do we say RL was? 6,000 and 7,200. So V in minimum required to turn it on is going to be 72,000 divided by 6,000, 12 volts. That is the minimum voltage that is required to actually turn on the Zener diode because of the values of the current limiting resistor and the value of RL. So your Zener voltage does not change. If you're designing a circuit, the minimum voltage will depend on basically the connection, on the value of the load resistance. Yes.
So by using voltage division, you're saying that the current through the voltage source is the same as the current through RL. So by that logic, you're saying that even though the Zener diode is turned on, there's practically no current going through.
Yeah.
Because it's probably so negligible that it's not going to.
Exactly. Yes. It's just, we're just barely turning it on. There, we are taking liberties, right? So all analysis is not perfect. If you're actually designing this for a circuit that you're going to use in real life, there are lots of other considerations that you have to take care of. And that's why there's large, variation. That's why some products on the market will be cheaper, some products are more expensive. And then we have military grade products where they're required to work at extreme temperatures, and temperature is a big. So whenever we say military grade, more often than not, it refers to like temperatures, extreme temperatures, like really, really hot or really, really cold. The way and why it refers to our diodes and electronics is because the voltage actually shifts. So the Zener voltage or the diode voltage will actually shift depending on the temperature. And if you remember the Shockley equation, the diode Shockley equation, that temperature change is linear. It's actually linear. I could go back in there, but I have to find a slide. Yes. So the cheapest rectifier circuits, like an adapter that will plug in the wall, as I've said, I've seen like circuits where they didn't even have like a PCB. It was just like diode components and just like twisted on, and that's it, and tape wound around it. And those cost like $5-6 or something like that, equivalent in US dollars. And so there's no design consideration. You simply they take like 4 diodes, twist them out, there's a capacitor and there's another Zener in front of it, and that's it. That's the cheapest. Other than that, that's the lowest end. Then I would think like the adapters that I'm using, this adapter right here, that is also simply, it's taking AC voltage and rectifying it into DC, but it has a lot of other extra protections built into it, like current protection, over voltage protection. We do not want, so your laptop, if my laptop requires 19 volts, output should stay at 19 volts, then I would have a Zener diode of like 19 volts, to regulate that voltage in there. Temperature wise, it will say if I use it, let's say in extremely hot conditions, I don't know, 50 degrees C is, obviously I'm not going to be somewhere outside in 50 degrees C, but if it does get that hot, that Zener diode voltage might shift. Instead of 19 volts, it might go to like 19.5 or even 20, who knows. And so that's a consideration. So that's, yeah, those are kind of examples. Let's see, where was I? So you're doing V minimum, right? 12 volts minimum. Make sense? How do you find the minimum voltage? So minimum, as I said, was rather, it's straightforward. It's just the amount of voltage that needs to turn on, and depending on your circuit configuration, you just calculate from the resistance that's required. Now, the other end, PZ max, maximum power dissipation of the Zener diode. It's not given to us, but we assume it to be 1 volts. And so therefore, IZ max, maximum current that the Zener can safely handle, will be 10 volts. Oh, sorry. 1 divided by 10, 0.1 amp, or 100 milliamps, which is a lot of current actually. Doesn't seem like it, but it is a lot. Now, IL has to equal VL over RL, so 10 over 6,000. And that is, how much is it? Where is my IL? Oh, there you go. 1.667 milliamps. So IL can never change. Remember what I said. IL should be fixed because load current has to be fixed. Anything excess has to go through the Zener diode, right? As the voltage from the input increases, the Zener diode conduction capacity increases. So it'll allow more current to pass through itself while keeping IL constant. So the maximum total current would simply be 101.667 milliamps. IZ plus IL, or IZ max plus IL. That's the maximum current that the source can safely output. Actually, or what Zener can handle safely. Right? So the maximum current coming from the source cannot exceed I total max. So this is IS, which is going through VR. So now I can calculate the voltage based off of the current values that we determined. So voltage across R would be equal to 101.667 milliamps times 1200. That comes out to be 122 volts. 122 volts. The maximum voltage drop that can occur across that 1200 ohm resistor is 122 volts. Yes. Oh, sorry. I don't know why it popped up. But the cursor just went there probably. That's why. Yeah, cursor just went there. And so the maximum supply voltage would be VR plus VZ, or VL actually, simply be 132 volts. So the VZ range what do you say, 12 volts? 12 volts to 132 volts. VZ. Oh, actually, sorry, VS. Yeah. VS. Supply voltage can range from 12 to 132 volts. If you have a Zener diode that can handle like 2 watts, now your maximum range is even more. So it depends on what your application is and where you need to use it. All right, questions. What time is it? 1:52. I do have 2 more topics, but yeah. Yeah, you can use this. Yes, absolutely. Yeah. Now this is just the maximum limit, right? 132 volts is not something that people have at their disposal. You can buy an adapter which can give you like 12 volts or 20 volts, 25 volts. 132, of course, I could build it if I wanted to, like order a transformer that can step down the voltage like there, and build it from there. But again, yeah, it's realistic. Yeah. Yes. Sure. So, oh, it skipped parts right there. So if you look at the circuit diagram, IS, the source current, is split between the Zener current and the load resistance, right? RL. So if you apply KCL at the top, we get IS is equal to IZ plus IL. So IZ plus IL. Now IL cannot change. IZ can change. So we found the maximum value for IZ, which was 100 milliamps. And then IL we found as 1.667. That 1.667 is the load current flowing through RL, which is constant or is supposed to be constant. And just add it up to IZ, and that gives us 101. That's the max that it can handle. Now, if you want to handle, as I said, if you put in a Zener diode in there that can handle 2 watts, then that would be 200 milliamps. I mean, yeah, 200 milliamps current handling capability. So that's the range. If we wanted to find, let's say, load current IZ. So for any given input voltage, and just taking it from the pre-lab, I think there are like 2. Can't remember exactly how many, but it's one is below the Zener voltage and one is above. Right? Remind me again. Is that correct? Right? Yeah, okay. So one is below, one is above. Below again does not matter. If the input voltage is below the Zener voltage, diode does not turn on. IZ is equal to 0. Right? Everything else, the voltage is going through the load resistance. All you do is you calculate the voltage drop across. So if the Zener is not on, all of the current is going through R and through RL. Just calculate the voltage drop across those two, and you find the current. So that's easy to, straightforward to do it. I should not be using the words easy, but straightforward. Now, if the Zener is on and you want to find, then IL obviously is simply the Zener voltage or RL. This time we won't put like a minus sign. We just take 10 volts divided by RL because that's what it's supposed to be. So 10 volts divided by RL gives you the load current. That should not change, of course. And then IS, the source current, would be VR over R, and VR would be VSS, supply voltage, minus VZ divided by that current. And IZ, of course, from KCL, we can simply write IZ is IS minus IL. Those are all the equations you need to actually analyze and design a Zener circuit. Okay, those are the only things you need. All right, questions? Any questions at all? Does the analysis make sense? Okay. What do you have next week? Transistor amplifier? Yeah, I'll try to cover a little bit on Friday so that y'all don't have to. If you'll get stuck doing the pre-lab, reach out to me. It's, you can reach out to your 361 instructor. You can reach out to me. I'm happy to help. Sorry, what? Next, yeah, that's fine. Absolutely, yeah. No, it's not a lab I teach often. I've done it 2, 3 years ago. It's been a while since I did it. BJTs, yeah, transistors. So is it just BJT characteristics? I'll take a look at it and I'll incorporate it. So 3 minutes left. I'll just talk briefly about the two circuits that we're going to do on Friday. Diode clippers. Basically, it clips off a portion of your signal. And then diode clampers basically clamps your waveform at a particular DC voltage level. So it applies a DC voltage and adds on to an AC signal. Anyway, these are the two circuits that we're going to take a look at. Jonathan, you asked a question. That's your answer. Zener and a regular diode in the same circuit. So it's clipper, straightforward. All right, I'll be in my office. I'm teaching a lab from 3 to 6. If you have a question, I'll be right opposite my office from 3 to 6. Stop by the office or in the lab room, it's fine. Otherwise, I'll see you all on Friday. Whoever's going to the career fair, good luck. All right, see you.